Hello algorithmicians. In this video I'm going to go through the application of the master theorem, but first another little skill which can come up in VCE algorithmics exams, where we're given a table of results and we're told to sort of estimate, work out the big O notation of these things. These tables here represent the number of operations, the size of the data that we're working with on the left, and then we've got some different algorithms and the number of operations which they take. And the way we're going to handle these, it'll often be multiple choice, so you know where to start. We're going to start with our best guess, and we're going to divide each of the numbers in this column by what we think our best guess is for this one here. So for my first one, suppose I think that it's linear. I try big O of n. I do 3 divided by 1, 40 divided by 3, 320 divided by 9, and so on. And I get these numbers here. And what you can see is that the number of operations is increasing when dividing by n. So this isn't going to be right, okay? Because we need to be able to have a number which we would multiply by n, some constant, which is always bigger than the number of operations. And that's clearly not going to work in this case. So we try something a little bit worse. We need to try worse time complexity. We might go up to n squared. And in this case, that works. We can see that the number's stabilizing around 4. It's an experimental set of data, so we're not expecting it to be exactly right. And we know, for example, with quicksort, in reality, the way it works depends on the pivot that we choose. But in this case, we can say it's big O of n squared because there exists some constant which we can multiply by n squared. In this case, it looks like it would be about 5, where 5n squared is always bigger than the number of operations it takes to process or apply our algorithm to data size n. So if that made any sense at all, try for the next one. Pause the video as you go along. If you want a little hint, we can see that b is not increasing anywhere near as high. So we're going to go probably even less than n. And the next one down on our hierarchy, log n. So here we try log n, and it doesn't really matter what base you choose, but I think given the numbers on the left, it seems intuitive to choose log base 3. And again, we can see that we stabilize out with some constant. So we can express this as big O of log n. We do not specify the base, we just say big O of log n. Right, try the next ones. For algorithm C, we can see that's getting pretty bad. And I mean, again, might take you longer or shorter time to get there. When we divide by 2 to the power of n, this seems to be stabilizing. It goes up, down a bit. So we can say that this one is big O of 2 to the power of n. Maybe you try the factorial first. For D, again, pause if you haven't tried it already. We divide by n. It seems a bit better, but this one seems to be going up still. So we try n squared. This one is more or less, well, it's consistently going down. So we wouldn't be sure about this one. Much more comfortable when we find that fluctuation. So what's in between n and n squared? N log n. So this one works out perfectly, which is unusual, but we can get that and say that is definitely better. Okay, moving on to the master theorem. Now, we've already talked about merge sort. We know, like intuitively speaking, for an array of size n, which is what we have here, we know we are going to have log n operations because we're halving each time. And at every stage, we are performing n operations. We're iterating through every set of data, every element in the array. And so we know we're going to end up with big O of n log n. That's what we're aiming for. Let's see how that works with the master theorem. And what do these numbers here, a, b, and c, represent? Now, I think b is the most intuitive. b, in this case, equals 2 because we are halving every time. A tells us how many subproblems we are creating each time, the number of times we recursively call this theorem is going to be 2. Okay, every time we halve the size of the data and then we make 2 subcalls. Now the KNC bit, this refers to the work that's done at each stage, sort of outside the loop, if you will. You often hear it's called outside the loop, but we mean at each stage of the operation. And in this case, we're doing n operations, or something to do with n operations, so C equals 1. That's because we're just looping through every item of data every time we do a step of merge sort. How do we apply the master theorem? We are comparing A with B to the power of C. So that's 2 with 2 to the power of 1, which we can see is equal. So we know we are working on the second case. So we have big O of n to the power of 1 log n. Of course, we're grown up, so we're not going to write n to the power of 1. We just write n log n, as we would expect. Now, first time you see this, you might think surely A and B are always going to be the same. If we divide it into 2, we're always going to have 2 subproblems, but that's not necessarily the case, as we know from binary search. Now recall how binary search works. We take a sorted array, we pick the middle number, and then we decide, is the middle number bigger or smaller than our target number? And that determines which side of the array we choose. So in this case, we're still halving each time, b equals 2, but we're only ever doing one call for each of those operations. So we halve it and we only choose one of those halves. In this case also, how much work do we do each time? We do constant work because each time we're doing 2 operations. We're finding the midpoint of the array and we're deciding, is our target bigger or smaller than that midpoint? It's constant, that means C equals 0, n to the power of 0. So we are comparing A with B to the C. So that is 1 with 2 to the 0. We can see that they are equal. So again, we're looking at that second case. We have big O of n to the 0 log n. That's an n, and n to the 0, of course, is 1. So we have big O of log n. Right, let's look at some just straight master theorem questions where we're given the recurrence relation. Incidentally, notice this line here. This isn't really of any consequence to us. VCE algorithmics, I think it's almost always going to be trivial. If you're writing a recurrence relation, make sure you write that line in as well. You write the base case. One could lose a mark there. Pause the video, try and apply the theorem. What you should have is A equals 2, B equals 4, C equals a quarter. We are comparing A with B to the power A with B to the power of C, so that's 2 with 4 to the power of a quarter. We know 4 to the power of a half is the square root of 4, which is 2, so 4 to the power of a quarter is going to be less than that. So we are dealing with the final case up here. We know this is going to be big O of n log BA, so log 4, 2. Log 4, 2 is a half, so big O of the square root of n. That's one we don't see very often. Let's try one more of those. Pause the video, try it yourself. We have A equals 9, B equals 3, C equals 0. If you put C equals 1 and you've done the work, stop, go back, change it. We compare A with B to the power of C. 9 with 3 to the power of 0, clearly bigger. We are doing that third case again, so we have big O of n log 3, 9, which is big O of n squared. Big O of n squared. There we are. Let's look at an exam question. Take a moment to read this. I'm just going to, as this bottom bit's got chopped off, it should be like C11, C12, C21, C22. Pause that, make sure you've read it. And we're going to try and explain the time complexity. You do well to write down exactly why you think it is what you think it is. So I think the easiest one is B equals 2, because the length of the matrix is halved each time. We know that A equals 8 because we are creating 8 sub-problems, which is to say 8 multiplications. The ambiguity here is that we do split the two matrices into 8 sub-matrices, but that's not what the master theorem is referring to. It's referring to the number of sub-problems that we create. So the number of times we do that recursive call, and we are doing 8 recursive calls. If you go back and look at merge sort and binary sort, it was the number of recursive calls that we do, not the fact that we've created 8 sub-problems is something of a coincidence in this case. And then we can say that C equals 2 because every time we are adding n over 2 by n over 2 arrays, so that means n over 2 squared operations, which is big O of n squared. We don't care about the fact that it's over 4. I think that last bit is particularly tricky to see, but it's the additions which are happening here at this part of the problem. Now, luckily, I think the second part is going to be straightforward. Even if we got the first bit wrong, A equals 8, B equals 2. Don't know why I'm writing it again. C equals 2. We are comparing A with B to the C, so that's 8 with 2 to the power of 2. We can see that that is greater. It means we're doing the third case, big O of log of n to the log 2 of 8, which is big O of n cubed. That's it. Enjoy.